We're going to begin looking at orbital diagrams. And an orbital diagram is just a way for us to show how the electrons are arranged in our energy levels and in our sublevels, in our orbitals. So this is what an orbital diagram is going to look like. This number here that we have out in front represents the energy level that we are in. The first energy level, remember, can only have one sublevel. It has the one S, and the orbital there is just an S, and there's only one shape, this sphere, so there's only one box. Again, then we move to the second energy level, and there's the S and the P sublevel. And again, the S sphere can only have one shape, but the P has that dumbbell shape, so we have the three different shapes that it could have, whether it's on the X, the Y, or the Z axis. So that's why there's three boxes there for that 2P part of our orbital diagram. So a few things that we need to remember as we start to, before we practice, is that electrons have to fill the orbital of the lowest energy first. So we're always going to start with 1s, because that's the absolute lowest energy level and sublevel that we have. And to help us so that we know what energy level and what orbital we should be in, there is a diagonal rule that has been put together. And this is something that you need to be able to draw. On a test, it might be very helpful. It's not going to be given to you. This is what the diagonal rule looks like. In the first energy level, we only have just the one S, notice that. And then each of these rows going across energy level 2 has S and P. Energy level 3 has S, P, and D. So every energy level kind of increases and we add another letter. Now the arrows tell you what order to follow. So 1s is the lowest energy, and then when you're done with the 1s orbital, then you move on to the 2s orbital. And then when you're done with the 2s orbital, you come back up here and start with 2p. And if we needed to, we would then continue to the 3s orbital, and so on and so forth until we have all of the electrons arranged that that particular atom has. So that is definitely something you need to be able to draw. You want to make sure that you have things in a straight line going down and going across. If you don't, then the problem is when you're doing your diagonals, if you have things not aligned very well, then you'll get your orbitals out of order. So be really careful when you're drawing that. The D and the F orbitals, notice that they didn't come in until quite a bit later. They have a lot more energy. They have quite a bit of energy, actually. And so the reason that sometimes those get skipped for a lower, or actually we'll go to another energy level, a higher energy level, but technically it has lower energy because the D and the F orbitals do require so much. And it's better to do that, to skip a certain sublevel like D or F, and go on to a higher energy level, but yet it actually has lower amount of energy for the electrons. That's why it's really important to follow that diagonal rule, so that you are always know for sure that you are putting your energy levels and your electrons in the proper order. This is also another way to represent this, and this, notice, has them the same as the diagonal rule if you were to look back at it. 1s, 2s and 2p, 3s and 3p, and then notice that we skip the d orbital temporarily and we go to the 4s orbital. We're going out of order energy level wise, but we are going in order from lowest energy first to highest energy, and that's the way you need to remember to do this. So that diagonal rule is really important. Also notice the number of boxes. The S, anything with an S only has one box, and that's because there's only one shape for the S. All of the P sublevels, whether it's the second energy level, third energy level, fourth energy level, there's 3 boxes for a P sublevel, and that's again because of the 3 different shapes. D orbitals always have 5 boxes because there were 5 different shapes, and if we ever get to the Fs, they have 7 boxes, and that's because there were 7 different shapes that the F orbital could be in. Alright, so some other rules. as far as filling up your energy levels. You want to go from lowest energy first to highest energy, and that is called the Aufbau principle, when we occupy the lowest energies orbitals first. So again, that's that electron diagonal rule. And then we always have two electrons together in a box if they need to be. But when we have to pair electrons, we want to make sure that they have opposite spins. So for instance, in one of those boxes, you would never want to put two arrows both going up or both going down. You would want to show the Pauli exclusion principle by having an arrow up and one arrow pointing down. And then our last rule is called the Hund's rule. And this is that the electrons are not going to pair together if they can avoid it. So let's say, for instance, we're in the same energy, maybe the 2p, and we have 3 electrons that we need to place in there. We would want to put each one in their own box, and then that would be our 3. Let's say we needed 4, then we would go back to the beginning and start to pair up our electrons. But this rule says that they seek to avoid pairing if there is a same energy orbital open already. Alright, so let's do some practicing. We're going to start with carbon. If you have a periodic table handy, you're going to notice that carbon has 6 electrons. So using all of the rules here that we just went over, we know that we have to start with our lowest energy first. We have 1s, and that is going to be able to hold a maximum of 2 electrons, and we can't seek to not avoid to pair those because there is just the 1s box there, so we have to put them together. Same in the 2s, we have to pair those together. So now we've used up 4 out of our 6. So that means that the last 2 have to go in this 2p orbital, and we have 3 boxes open. So we are going to want to, following our Hund's rule, that those electrons are going to avoid pairing together. We're going to want to keep those separate. So this would be carbon, 1, 2, 3, 4, 5, 6 total electrons. We followed all of our rules by lowest energy to higher. We have 2 electrons if they're in the same orbital. They have the opposite spins, and we have avoided pairing them together like we did in the 2p orbital there. So now let's try chlorine. This one has a few extra electrons. If you look at your periodic table, chlorine has 17 electrons. So we have more of those arrows that we're going to have to place this time. But again, you're always going to start with the 1s. So again, we're going to have 2 electrons that need to go there. And then we move up to higher energy where the 2s is concerned, so it can also hold 2 electrons. And now we have the 2p orbital, and this time, since we have 17 electrons, we're going to need to use all of these. Each box can hold 2 electrons, and I'm showing the opposite spins. So we have 2, 4, 6, 8, 10 electrons total that have been used up right now. So that means I have 7 left, so I'm going to put 2 more here, so that takes me up to 12 electrons. This up here is just my own personal notes. It's not anything that you have to write, but it's just a way for me to keep track of the electrons that I've used. I have 5 left. We need to make sure we're following the Hund's rule here, where we don't pair them unless we have to. So we have 5 electrons. We would want to put 1 in each box. And now we don't have a choice but to start pairing them together. So we have 12, 13, 14, 15. So actually we don't have to pair them together at all. They will stay unpaired. 2, 4, 6, 8, 10, 12, 13, 14, 15. 15. We have 17. Okay, I can count. So 15, and then we have 16 and 17. So yes, we do need to pair 2 of them. Oh, gracious. All right, so there's our 17 total electrons that we need for chlorine. All right, moving on to magnesium. Magnesium, if you look at your periodic table, is going to have 12. So let's erase all of this here. And again, we know that it has 12 because it should be the same as our number of protons. We don't have any plus or minus charges here. So magnesium has an atomic number of 12, which means it has 12 electrons. So again, we have to start with 1s. We have to put our 2 in there, going opposite spins. And now we have 4 electrons being used up. And that takes us to the 2p orbital. And so we're going to need all 6 of those. Now we're at 2, 4, 6, 8, 10. And we have 2 electrons left, and so that means that we need to place both of those opposite spins there in our 3s orbital for our total of 12 electrons. We didn't need the 3p orbital at all for that one. Lastly, we have fluorine, and if you take a look at your periodic table, fluorine is at 9 electrons. And again, we start with the 1s, lowest energy, moving our way up to higher energy. We're at 4 electrons now. And so this would be 5, 6, 7, and then 8, 9. We don't have a choice but to pair some of those, but we did follow the Hund's rule by not pairing them until we had to. So that would be our 9 electrons, and we wouldn't need the 3s or 3p at all in that case. So that's how you do an orbital diagram. Those 3 rules, Aufbau principle, Pauli exclusion principle, and Hund's rule, are definitely 3 that you will be hearing about a lot as you do different practice problems.